Welcome back. Let's have some more fun with annuities. So what I want to do is I want to explore the value of a fixed income security, which we denote as P at a particular point in time. And in fact, I want to look at this if this security might be just issued. Yeah, let's just denote this as P0. So it's let's talk about this like the current value, so to speak. That simplifies the notation. Let's assume I have a fixed coupon payment, and the coupon payment is C, and it's paid over several periods. And what I do then is I do some discounting. Yeah. So J runs from 1 up to capital T. Capital T would be your maturity, and I discount with an appropriate discount rate, which I denote R. Yeah. So when that goes to the power of J. Yeah. So R is a discount rate, which is of course strictly positive, and that would be the value of my my fixed income security at the current point in time, which I denote 0. You can also denote it differently, but then you have to adjust your equation. So actually what that states is the value of a fixed income security is the coupon payment starting right now, going up to the future, up to maturity. But this future payment, of course, has to be discounted with an appropriate discount rate. Now, can we say something more about this term here, the second term? Is it possible to simplify that? And I want to show you that this indeed is possible. The first thing which is useful to do is to simplify the notation by taking a substitution. So just denote rho, Greek letter rho, is equal to 1 divided by 1 plus the discount rate, and obviously for an appropriate discount rate this is less than 1. Yeah, so that's my discount factor. If I use that, then I can simply write this as follows. I have again my constant coupon payment C, and then in rectangular brackets I would get rho plus rho to the power of 2, and so on and so on, and it would go all the way up to rho to the power of capital T. Okay. The next thing I want to do is I want to look only at one part of this equation, because C is a constant. Yeah, so it's not massively interesting. So now I just want to look at the value of the second part, which I denote K. You can denote this as you wish. By writing actually down this, I implicitly assume that K really exists. Yeah. Now that is usually the case, but not necessarily the case. But this is basically what we implicitly assume. But we don't have to be too strict about these things. We are doing finance. We are not doing mathematics really. Okay. Good. So now let's explore this a little bit further. So for instance here, what you could easily do, it's perfectly permitted, is you could simply multiply by rho. So you can do something like rho K, which would be well, rho to the power of 2 plus rho to the power of 3 plus and so on and so on, plus rho to the power of T plus 1. Okay, so that's perfectly fine to do. Then of course what you can also do, because you're free to do this, is you can add rho and subtract rho. Yeah. Of course now you might argue this is rather stupid, but you will see in a minute that actually this is a little bit helpful, because now what you have in here is you have K again on the right hand side. Yeah. To see this this term here, all of these terms up to the term rho to the power of T, which is in here, is just hidden, this would be again K. Yeah, and this is exactly what we exploit. Good. So what I can do now is I can rewrite this as follows. This is rho K and then I obtain k again plus rho to the power of t plus 1 minus rho. Yeah, so that would be permitted to write it like this. Good. Now if we look at this equation, we could now of course try to simplify that. So ideally I would move all the k's on one side, which I could do moving the rho k to the right hand side. I can then also flip sides to again get k on the left hand side. It's just out of convenience. So I can write k minus rho k. So basically moving rho k on the other side and then switching sides, so to speak. So that is a possibility. And then we would have here rho minus rho t plus 1. Yeah, so that would be the way to do it. Good, then we could simplify this further. So that of course is then written as k is equal to, I can take the rho out of the equation on the right hand side, so I get rho, then 1 minus rho, and I obtain here 1 minus rho to the power of t. Good, and now the only thing left is I have to substitute this back. So I obtain then the following. It's k equal to, and I have here 1 divided by 1 plus r, and 1 minus 1 divided by 1 plus r, and here we have 1 minus 1 divided by 1 plus r to the power of t. Here we are, so we are all almost done, and then I obtain k. If you simplify that, you see, put it on the same denominator, so it's 1 plus r divided by 1 plus r minus 1, which gives r, and then the 1 plus r cancels, so you get 1 divided by r, 1 minus 1 plus r power of t. Yeah, so this is basically what you obtain. Good, and now we just use that back in our equation all the way up there. So then I can simply write the value of my fixed income security at the initial value time 0. That would be simply then my coupon payment divided by r. Actually, this part would be a perpetuity. So if it continues forever, that would be the value. But obviously it doesn't continue forever. So the second part is then of course driven by your maturity. Yeah. So 1 plus r power of t. Yeah, and we are done. So that's a nice way to simplify this expression. It works of course only under certain conditions. You have to have always the same discount rate and so on. Otherwise of course you have to go into some numeric work, which we will do later. Good, I see you in the